Okay, so hi everyone, welcome to another MLFL. And today we are very excited to host Professor Gauri Joshi. Professor Joshi is an assistant professor in the ECE department at CMU since September 2017. And her research focuses mainly on stochastic modeling and analysis for ML infrastructure and the cloud. Before CMU, she was a research staff member at IBM TJ Watson Research Center. And she completed her PhD from MIT EECS in June 2016, advised by Professor Gregory Warnell. Before that, she got her BTech and MTech in electrical engineering from IIT Bombay. She has won numerous awards and honors for her research, including most recently the NSF Career Award in 2021 and the Sigmetrics Best Paper Award in 2020. So without further delay, let's get started. If you have any questions, please feel free to put it in the chat or raise your hand, and I'll interrupt Professor Joshi to ask the question. So Professor Joshi, over to you.
Thank you so much for the invitation and for the introduction, Kalpesh. So as Kalpesh said, please feel free to stop me if you have any questions during the talk. Today I'm excited to present this latest work from my group on tackling computational heterogeneity in federated learning. This is joint work, which is led by my PhD students, Jianyu Wong and Yeji Cho, and master student Hao Liang. And this is also with several collaborators from Princeton and Google who are listed here. So as many of you might have heard, federated learning is this emerging machine learning paradigm where machine learning training is done on resource-limited edge devices such as cell phones, and heterogeneity, both in the form of data and computational capabilities of these devices, is a major challenge in federated learning. So in this talk, I will first introduce federated learning for those who may not be familiar, and then discuss two works on tackling computational heterogeneity. Firstly, in terms of devices having different speeds of computation, and secondly, in terms of devices being only intermittently available to do training. So that's the outline of the talk. Now, let me start off by talking about distributed or federated learning algorithms. And when I say that, I actually mean stochastic gradient descent or SGD, because machine learning training today is synonymous with using SGD. It's the most commonly used optimization algorithm. And at its core, it is very simple. It involves minimizing an objective function as shown here. This is the empirical risk function, which is the average of the losses, F, at all the n points in our training data set. And the way we optimize the model parameters, which are represented by the vector X, is that in every iteration, we take a mini batch of B samples, compute gradients for those B samples, and take a step along the direction of the gradient descent with a learning rate eta. So this is the simple SGD update. And as you can see, this is inherently sequential. But for large training data sets, running it at a single node is prohibitively slow. So it is imperative to distribute this across multiple nodes. And in most standard implementations of machine learning training for large data sets, this task of computing gradients and updating the model is generally split across multiple worker nodes and a parameter server. So this is called the parameter server framework, which is used for training machine learning models in the data center setting. So here, the training data set is shuffled and then equally split across the worker nodes. And then we have a parameter server to aggregate gradients coming from these nodes. So in each training iteration, these worker nodes would read the current version of the model parameters from the server. Then they will sample one mini batch of data each from their training local training data set, and then compute gradients on that batch, send back the gradients, and the parameter server will then aggregate these gradients, will just average them, and then apply this SGD update. So what we can see here is that as you have more and more workers, we can process more data per iteration, and that will result also in this gradient becoming less noisy, which will lead to better conversions. So we want to be able to scale this framework to many workers. But it is hard to do that in practice because there can be synchronization delays in waiting for slow or straggling workers, or also communication delays on these links between the parameter server and the workers. So this can be a hurdle for the scalability. And over the past few years, there have been many works on improving the scalability of this framework, including some works from our group, such as asynchronous SGD, or doing local update SGD, or overlapping the local computation and communication, and so on. So in spite of all of these works to improve scalability, this framework itself has some limitations. So first of all, it assumes that these worker nodes are servers in the clouds, which are typically homogeneous and available throughout the training process. And secondly, which is a more important limitation for the purpose of this talk, is that we assume that there is a centrally available training data set that can be shuffled and then evenly partitioned across the worker nodes. And this assumption breaks down in many modern applications where data collection is done at the edge. So in modern applications, you have cell phones, tablets, sensors, etc., which are collecting data from their environment. And these data are highly informative. They can be used to train machine learning models. So for example, whenever we type something on our smartphones, there is a next word prediction service which uses language models to predict the next word that a user may type on their phone. And in order to train these models, if we just use the parameter server framework that I described earlier, we would have to send all of the training data to the cloud. And this can be very expensive and slow because firstly, these devices are resource and bandwidth limited. There are also many of these devices. Moreover, there can also be privacy laws that forbid sharing of sensitive user data with foreign servers. So for example, if we are typing something on our smartphone, we may not want that information in a raw form to just be sent over to a cloud server that we may not trust. So federated learning is this emerging framework that is designed to operate within these constraints of edge-based data collection and training. So the core idea of federated learning is that whenever we want to use edge data for training machine learning models, we keep the data at the device. And instead, we bring model training to the edge. So in each round of federated training, these edge clients, which have collected different data sets on their own, will read the current version of the model from the central server. They will do a few local updates. They won't just compute one gradient, but they will do multiple local gradient steps using their local data. And then these updated models will be sent to the central server, which will aggregate them. So by keeping the data on the device and only sharing the model, we can get better communication efficiency as well as better privacy guarantees. So this is the high-level idea of federated learning. Now, by looking at this picture, you may think this looks very similar to the parameter server framework. How does it differ from it, and what makes it challenging to design algorithms to train machine learning models in this framework? So it does look similar, but there are some subtle yet important differences. So the first major difference is that unlike the data center setting, here data is inherently heterogeneous across devices because these data are collected by the edge devices and they can be different both in size as well as composition. Secondly, the computation speeds of these edge nodes might vary across clients. And these are not just short-term fluctuations as we would see in a cloud setting, but these can be consistent long-term asymmetry in terms of their computation speed. So for example, if some of these devices are cell phones and some of them are tablets or computers, then they can have widely different computation capabilities. Another difference is that due to communication limitations, these devices can only send infrequent updates to the parameter server. So we need some way of reducing the frequency of communication. And next, the scale of this system is an order of magnitude larger than the data center-based training. So instead of data center-based training, where you may have tens or hundreds of worker nodes at most, here you can have thousands or even millions of these client devices, which are distributed all over the world. And because of this scale, only a small subset of these edge clients will be available for training at any given time. So these are some of the main differences between federated and data center-based training. So I hope all of you get that. If there are any questions, please feel free to stop me. So now that you understand at a high level what federated learning is, let me go into defining the optimization objective and the algorithms that are used in this setting. So first, let us define the local and global objective functions. Each device has a local objective function, which is denoted by Fi. So this is just the empirical risk function computed on its local data set, Di. The global objective function, which we want to minimize, is a weighted average of these local objectives, where they are aggregated in proportion of the data set size. So this PI is the fraction of data that is present at the ith edge client. Now you might wonder, why do we aggregate these local objectives in this proportion? The reason is that we want to emulate a data center-based training. So ideally, we would have sent all of this data to the central cloud server and done training in the cloud. And in that case, the ith client would have contributed size of DI data to that entire training data set. So to account for that, we assign this weight PI to the ith client's objective function. So our goal for this talk is to find a single model that minimizes the global objective f of x. So there are some other works which consider variants of this objective, such as training personalized models at the different clients, or trying to be fair to different clients. But for simplicity in this talk, we are going to just focus on this one single global model training objective. So from this definition, you can also observe that the local and global objectives can be very different depending upon the composition of these data sets Ti. And this can affect the convergence of federated training algorithms. So we'll see that in the next few slides. So for these local and global objective functions that I defined, let me describe now to you the standard federated training algorithm, which is called FedAvging. So this algorithm divides training into communication rounds, where in each round, you send the current model to the set of available clients. This can only be a subset of the clients. And then these clients do tau local steps of SGD. And because they have different local data sets, these resulting models that we'll have at the different clients will differ from each other. And they can drift away from each other as you increase the value of tau. So after doing these local updates, the clients will send these models back to the server which will then aggregate them in this proportion of pi assigned, the weight pi assigned to the ith client. So this is the algorithm. Now, the question that we want to answer is, how does this algorithm work in the presence of data and computational heterogeneity? So what if there is data heterogeneity where these model versions can drift away from each other as they do more and more local computation? Or what if there is computational heterogeneity where each client does not do just tau steps, but the tau can vary across clients? And finally, what if only a subset of these clients are available in each round? Then how can we optimize the objective function? So these are the challenges that I'm going to mention during my talk. So let me talk about data heterogeneity first. So I'm going to only briefly mention this because this problem has been tackled by many works recently, and there are several approaches to tackle this issue. So to understand data heterogeneity, first let's see what happens if we vary the tau, which is the number of local steps. So if you think about it in terms of communication efficiency, then increasing tau is really good because we perform more local computations at these edge clients and less frequent communication with the central server. So within the same number of communication rounds, using a larger tau will result in completing more iterations of SGD, where each iteration is counted as one arrow or one step of SGD done at the local clients. So large tau seems to be a good choice for communication efficiency, but can it adversely affect the quality of the solution? To see that, let's look at a toy example with just 2 clients, and then look at what happens in 2 extreme cases. First, where tau is just equal to 1, and the other extreme case where tau takes a large value. So here I'm illustrating by these dots different points in the parameter space. This is the current version of the global model. X1 star is the optimum of the first client's local objective function. X2 star is the optimum of the second client's local objective. And X star is the global minimum that we want to reach. Now, if we start doing federated averaging with tau equal to 1, then what will happen is that in each round, client 1 will take one local step, which will roughly go towards its minimum. Client 2 will take another step, which will go towards its own minimum. And then we average these, and this averaged gradient is used to update the global model. So if we repeat this process, we can see that the global model is gradually going towards X star. And we can show this. So we can show that this algorithm becomes equivalent to synchronous SGD because this average gradient that we have is an unbiased estimate of the true gradient of the global objective. So all is good when tau is equal to 1. But what will happen if tau is very large? So what if each client takes many local steps? So here we are illustrating where each of these 2 clients takes many local steps, and as a result, they will reach close to their own local optimum values. So this might seem good because we are making swift progress towards the client's local optimum in just one round. But let's see what happens when we average these models. If we average these updated local models, then the global model will move here, which seems good. But now in the next round, we will start off with this global model, and again, the clients will do local steps. And again, they will go back towards their own local optimum. So once we average these, again, we will end up somewhere close to this point. So effectively, we are stuck at this point, which is the average of the local minimum. And because this objective function is nonlinear, this average of local minimums is not equal to the global minimum. So what we see here is that large tau will result in fast convergence, but the convergence will be towards an inconsistent solution. It will be towards an average of the local minimums rather than the true global optimum value. I hope this example is clear. So we can also formally analyze convergence and show that the error after T communication rounds is as given here. This is for a decaying learning rate. And there are two key terms here. The first term decreases with tau, which is the number of local steps. So this is because we are able to complete more iterations within the same number of rounds. But the second term here increases with tau. And this is because of the discrepancy between the models. And the second term also increases with the amount of data heterogeneity, which is captured by this parameter kappa. So the kappa measures the difference between the local gradients and the global gradients. The more exact definition of kappa is given in our paper. So you can take a look at that if you're interested. So the takeaway from this is that this second term will become 0 only when tau is equal to 1 or if there is no data heterogeneity. And the first term will decay with tau. So in general, if you have a large value of tau, it's good at the beginning, but then later on, it can lead to a high error flow. So how do we make sure that we choose tau correctly such that we get fast convergence in terms of communication rounds, but we also get a low error flow? So some of the solutions that have been proposed include choosing a small enough tau or small enough learning rate so that these models don't drift away from each other, or using proximal methods that pull back these client models towards the server model to stop them from drifting away. These solutions work, but then they also slow down convergence. So another option is to define some kind of adaptive strategy where you start off with a large value of tau and then gradually decay it. So this is true for a fixed learning rate. If there's a variable learning rate, then this tau schedule can also be changed accordingly. Besides these, there are also other solutions such as variance reduction techniques that work very well to tackle this data heterogeneity problem, but then they require additional communication or computation or memory at the clients or the server. So I just wanted to give you a flavor of the data heterogeneity problem in this first part of the talk. Now I'm going to move on to talking about computational heterogeneity, which is the main focus. Are there any questions at this point?
I think we can move on.
Okay.
I don't see anything on the chat or hand raise. So
sounds good. Feel free to stop me if you have questions. So let me talk about computational heterogeneity next. So what do I mean by computational heterogeneity? First, let's talk about the sources where heterogeneous local progress can come about in federated learning. So when I described to you the FedAvg algorithm earlier, I said that each client does the same number of local steps. However, in many FL implementations that are deployed already, clients don't do the same number of local updates, but rather they do the same number of local epochs. So epochs means traversals of the local training data sets. And because these local data sets are varying in their size, what this will result in is that clients which have more data will do more local steps, and clients which have less data will do less local steps. So this is one source of heterogeneity. Now, another way to implement the federated averaging algorithm, which is more straggler resilient than the original approach, which has to wait for all the clients, is that we could fix a local update time window and then let clients do as many local updates as they can within that time window. So faster clients will do more local updates, slower clients can do less local updates. And this will also result in computational heterogeneity. And finally, even if the number of local steps is fixed across the clients, they can have different local optimizers. So maybe some of them use variable learning rate schedules, or they use local momentum or adaptive optimizers, etc. And these differences in the local computations can also lead to heterogeneous local progress. So the main thing to note here is that current implementations disregard such heterogeneity. So even if clients do different numbers of local updates, they just aggregate these updates in proportion of PI, which is the fraction of the training data set at each client. And this kind of naive aggregation can lead to some serious inconsistency issues. So to illustrate that, let me show you an example again with two clients. If we consider a homogeneous setting where, again, you have a global model, you have these two local optimas and the global optima, then if each client does the same number of local steps, the global model moves towards the global optimum. So as long as the number of local steps are small enough, we can ensure that the global model will converge to X star. And this is a consequence of the convergence bound that I showed a few slides ago. However, if we have a heterogeneous setting where client 1 does many more local updates than client 2, then by averaging these two models, we'll get a global model that goes in this direction. So because of this, as you can see, the solution will be biased towards the clients which do more local updates. And this bias cannot be fixed using the techniques that we looked at to tackle data heterogeneity. That's because this is a consistent asymmetry in the local computations at the clients. So to understand the convergence properties in this heterogeneous setting, in our work, we proposed and analyzed a generalized version of the Fed-averaging algorithm. This generalized version is called FedNova. And then by this analysis revealed that in the homogeneous setting, we are optimizing the true global objective, which we intended to optimize. But if we do heterogeneous updates like this and naive aggregation, then what we end up minimizing is a mismatched global objective, which is given by this. So here you're mixing the local objectives in a different proportion than the size of the local data set. And then clients which do more local updates will get a higher weight here. And this mismatched or surrogate objective can be arbitrarily different from the true global objective. So this observation also led us to a correction algorithm. So at the time of aggregation, we can make sure that these weights that we are assigning to updates coming from different clients are set in the right way so that there is consistency between the global objective and the objective that we are minimizing. So let me tell you about this generalized Fed averaging framework and then show you how we did the correction to the heterogeneous local update case. So recall that this is the standard Fed averaging update rule, where you start off with some global model. Each client does local updates, and this accumulated local update at the client, let's denote it by delta I. So the global model is updated as per this equation, where we are just averaging the accumulated local updates and then adding that to the previous version of the model. So we generalize this vanilla update rule in two different ways in order to subsume heterogeneous local progress methods. The first generalization is that in the original update rule, this delta I is just the sum of the local gradients times minus the learning rate. but instead we allow this to be any linear combination of the local gradients, where these weights of the linear combination are denoted by the vector AI, and these AIs can also be different across the different clients. So this is the first generalization, and this allows us to subsume several different local optimizers by choosing different values of this linear combination weight vector AI. So for example, FedProx corresponds to setting AI like this, or doing local momentum SGD would correspond to setting AI like this. And the vanilla Fed averaging update rule is also a special case. So that was the first generalization. The second generalization is that when the server is taking an average of these local updates, instead of just taking an average of delta I, we take an average of normalized versions of delta I. So we take delta I, the local progress at each client, which is denoted by this now, the generalized version, and then we normalize it by the L1 norm of AI. And DI is denoting the normalized accumulated update or normalized gradient. And the update rule replaces this delta I with DI. And finally, we also allow this weight PI to be set to any arbitrary weight WI, which can be set by the server. So by putting all of these together, we'll get this new version of the update rule, which has three key components. The first is this normalized gradient, which takes these local steps and normalizes them by the number of local updates, for example. And this normalization is determined by the choice of the client optimizer. Secondly, you have these aggregation weights, which determine the direction of this averaged vector. So these green arrows are the normalized gradients, and when we average them at the server, we'll get this average gradient. So the direction of that gradient is determined by these aggregation weights. And then finally, you have this parameter called the effective steps per round. And this just denotes this just controls the magnitude of the global update. So you can think of this as a global learning rate. So this generalized update rule optimizes an objective function, which is given by this. So this is simply the weighted sum of Fi, where the weights are Wi. And a special case of this framework is the original Fed averaging case, where you set all the AIs to be equal to each other, all the AI vector elements, and Wi as this and tau effective as this. So what FedNova does with this correction mechanism that we'll propose is simply to fix these Wi, the aggregation weight. So whenever we aggregate updates coming from the clients, we make sure that first of all, they are normalized. And once they are normalized, we set Wi as equal to Pi. And this small change in the aggregation step allows us to ensure a consistent solution. So let me show how exactly this normalization and aggregation happens through this example. So here we have a heterogeneous case, and this left-hand side is showing the regular Fed averaging update rule, where you just average these updates in proportion of Pi. Instead, in FedNova, what we propose is that you take this local accumulated gradient, which is delta I, and then normalize it by the number of local steps. So here, because the first client is taking 4 steps, we divide this accumulated update by 4. And similarly, this we divide by 2 to get these normalized gradients shown in green. And then we just average those gradients in proportion of Pi. So the FedNova update rule will be this. So you'll take the normalized accumulated update and then average them in proportion of Pi. And then this tau effective is a scaling factor that will compensate for the fact that we are normalizing these local gradients and then reducing their magnitude. So this new update rule optimizes the true global objective which we wanted and ensures consistency. So we also have a convergence analysis. In the paper, I won't show the details, but at a high level, the error contains two terms. The first term is a vanishing error term, which is similar to the Fed averaging analysis that I showed earlier. And we have a second term here, which is a non-vanishing error term, which is a result of the data the model aggregation procedure. So if our aggregation weights Wi don't match with Pi, as we enforce in FedNova, we force Wi to be Pi. If we don't ensure that, then there will be this additional error term, which will increase with the amount of data heterogeneity. So this term is zero only if there is no data heterogeneity, or if we choose these aggregation weights correctly. So overall, this analysis provides new insights into existing algorithms like FedProx and local momentum, etc. So those algorithms can also be analyzed using this general framework. And it provides a way to ensure fast convergence and a low error flow. So here are some results that compare Fed averaging and Fed Nova and Fed prox. So Fed averaging is the standard algorithm shown in blue. We can see that it converges to a higher error floor because of this inconsistency problem, whereas Fed Nova gets a much better convergence.
Professor Joshi, we had a question.
Sure.
So I think it was on the previous slide, and the question was, how is the number of local steps on every client determined? Like, how do clients decide their respective tau
Okay,
values?
I see. So as I showed at the beginning, there are these different sources of heterogeneity. So it depends on how you're implementing the local computation at the clients. Suppose we fix the number of local epochs that will be done at each client, then the number of local steps will be proportional to the size of the data at that client. On the other hand, if we fix a time window and allow fast clients to do more updates, slow clients to do less updates, so the number of local steps will be proportional to the computation speed at the client. And note that the number of local steps can also vary across rounds. So a client which is fast at the beginning may slow down later on and do less local updates in a round. And that can also be handled by this generalized framework. I hope that answers the question.
Yeah, I think we can move on. There's no reply on the
Right.
chat.
So this tau bar here is the average of the local steps done by all the clients in each round. All right. So this table here shows the test accuracy if we use the Fed averaging aggregation or the Fed Nova aggregation. So here the only thing we are changing is the way the updates are aggregated, and the client optimizer can be anything like vanilla SGD or momentum SGD or even variance reduction method. So Fed Nova is compatible with all of them. And in many cases, we can see that it gives almost a 8 to 10% accuracy improvement just by ensuring consistency of the solution. So when I mentioned heterogeneous local progress, I discussed these two sources, and these are covered by FedNova. But then what if you use different other local optimizers? So local optimizers such as Momentum or FedProx are covered by FedNova. But one might want to use adaptive optimizers such as Adagrad or Adam that give much faster convergence to the local optima. But these adaptive methods are currently used only on the server side. And that is because if we use adaptive local optimizers, then the local progress will depend on the local Hessians which are heterogeneous across the clients. And this can lead to the inconsistency problem similar to what we saw before. So this is illustrated in the example here. The blue curve is the standard Fed averaging, and the green curve shows a case where the clients do local adder-grad. So the benefit of adder-grad can be seen at the beginning. You get this sharp drop, but then it converges to a higher error floor than Fed averaging. And this is because of the inconsistency problem. Sorry, there's a train going by my office, so you'll hear some noise. So this solution bias is due to the heterogeneity caused by adaptive local optimization. And the framework that I proposed earlier doesn't directly work here because it only works where the accumulated update is a linear combination of the local gradients, and we can write it like this. But in adaptive methods, the accumulated update depends on the local preconditioning matrix, which are dependent on the local Hessians. So you'll have to write delta like this, where A is a matrix rather than a vector. But we are able to generalize our analysis to that case and also generalize the correction method. So in a follow-up work, we showed that you can normalize the gradients using this local correction matrix. And at the server, when we average the updates, we can use this global correction matrix, and a combination of these can make it work with local adaptive optimization methods. So that was about the second part of the talk, where the amount of local computation or progress is varying across the clients. So the last part, which I'll go over briefly, I think I have about 15 minutes left, is on intermittent client availability. So at the beginning, if you remember, I mentioned that the number of these edge clients can be thousands or millions, and only a small subset of them will participate in each training round. So now we are trying to understand how to select that subset, and can we select it in such a way that we get better convergence. So currently, most works on analyzing or designing federated optimization algorithms consider that out of the set of clients which are available, a subset of them is selected uniformly at random with replacement. So this ensures that for the selected subset, if we consider this effective objective function, which is the sum of the objectives of that chosen subset, this is an unbiased estimate of the global objective function. So unbiased selection ensures that the expectation of this effective objective is equal to the global objective. And most works consider this scenario, and many prior results which do convergence analysis and algorithm design for the full client participation setting can be extended to partial client participation, but only in this unbiased selection case. However, what we wanted to explore is it always good to do unbiased selection? What if we preferentially select clients which have high local losses, for which in other words, the clients for which the current global model is not working well, and can it improve our conversions? So to see that, let's look at an example with just two clients. So this F1 and F2 are the local objectives of those clients, and f of x is the global objective. So if we do this unbiased random selection of just one client in every iteration, then whenever we choose a client, we take a step along the direction of descent on that function. So for example, if we choose client 2 initially, then we move along this F2 function, then again we choose client 2, we take one more step down on the F2 function. Now in the next iteration, suppose we choose client 1, then we can go downwards along this F1 function. So you can see that it switches back and forth between F1 and F2. And although this might work in expectation, there are cases where it can cycle through the same steps again. So here you can see that it reaches almost close to the minimum of F1, but in the next step, it can go back here if we choose F2, because this point has a pretty high value for F2. So these kind of cycles can happen if you do unbiased client selection. On the other hand, suppose we do biased selection, where whenever F1 is larger than F2 at the current X, we choose client 1. And whenever F1 is less than F2, we choose client 2. So if we do that, let's say we have the same starting point, then because F2 is larger here, we are always choosing client 2 and then moving downwards along that function. And only at this point, whenever F2 goes below F1, we switch to F1 and then take this step. So you can see that here in these 5 steps, we reach close to the global optimum, whereas here we might cycle back and go back to the initial point. So this might seem like a carefully constructed example to show that random selection doesn't work, but this can happen in practice, and biased selection does indeed improve the convergence. So biased selection towards higher loss clients does give faster convergence. But because it is biased by definition, it will lead to some skew in the objective function that we are optimizing on average, and it could lead to a higher error flow. So to understand that.
Professor Joshi, we had a question on the previous slide. It was a clarification, so I interrupted. So how could F1x on the right side of the local, how could F1x be on the right side of the local minima? I thought its position is determined by f of x.
Right side of this, so you mean this and this?
Yeah, I'm not sure. Kirk, do you want to unmute yourself and ask the question?
Yes. So so if we look at the arrow of the F1x curve, it is on the right side of the local minima, right?
Yeah.
Yeah.
You mean global minimum, X star? X star is the global minimum.
Oh, okay. Maybe I'm misunderstanding it, but
yeah. So this is X star is the global minimum, and but we are not directly optimizing f of x, right? We are either optimizing F2 or F1, and f of x is a average of them. So if we optimize F2, that is, we keep on selecting client 2, then we'll go downwards along this curve. But then if we switch to client 1, at that point, you will now move at that X, you find F1 of X and then move downwards along that curve.
Oh, okay, now I see, thanks.
Sure. So to understand the effect of bias selection, we came up with an analysis framework where we measure the selection skew of any client selection policy through this parameter rho. So there are lots of notation here, so I won't give you all the details. But the main point is that this parameter rho captures the skew of a selection policy. If rho is equal to 1, that means we are doing unbiased client selection. If it is greater than 1, then that means you are biasing towards clients with higher losses. And if it is less than 1, we are biasing towards clients with lower losses. So what we can show is that if this rho is greater than 1, then we can get a faster convergence rate. So in this convergence bound, we can get a rho bar in the denominator, but it can lead to a solution bias, which is also proportional to the value of the selection skew, as well as the amount of data heterogeneity. So there is a trade-off in terms of how much you bias. So maybe we should adaptively change the bias through the training process. So motivated by this, we can design a biased client selection scheme where you can tune the selection skew as you want by just changing one parameter. So this client selection strategy is inspired by something called the power of D load balancing framework. This is used in randomized algorithms or queuing systems or scheduling algorithms. So the way we use it in federated averaging is that instead of just selecting clients at random, we will first sample a candidate set of D clients at random using unbiased selection. And then for these D candidate clients, we estimate their losses. So we try to find what are the local objective function values. And then out of these candidate clients, we select M clients, which have the largest losses. So for example, here, if we want to choose one out of those 3 candidate clients, then we would just choose F3 because this has the highest loss among these. So in this scheme, you can see that by choosing the value of D, we can control the bias. If you set D equal to M, then it is just unbiased selection. On the other hand, if D is larger than M, then we are introducing more and more selection skew towards higher loss clients. So this idea is also connected to the so-called importance sampling techniques that are used in just standard SGD setting. And these techniques have also been shown to give convergence improvements. So we can show through experiments that this power of D-selection framework indeed gives faster convergence. So you can see that as you increase the value of D, we get faster convergence as compared to random client selection. However, it can come at the cost of a slightly higher error floor. We can also come up with a way to make this method more efficient. So you can see that in step 2, we have to estimate these local losses, which can be pretty expensive. So we have some computation and communication efficient variants of this method that can give almost the same performance with lower cost. And these are some plots that show that the left-hand side is where there is less data heterogeneity across the client. So in that case, the power of D schemes, these are the 3 schemes. The power of D is the original one, and C power D and R power D are the more efficient variants. So they do give better test accuracy and also lower training loss. But this gap increases as you increase the amount of data heterogeneity. So if there is more heterogeneity across the clients, then in fact, this bias selection scheme does even better. So that was the last part of the talk. I'm going to conclude here. I hope this talk gave you a good flavor of federated learning and the challenges that it poses. So in this talk, we covered data heterogeneity, computational heterogeneity, and client availability. But there are many other interesting problems in this area, such as personalization, fairness, or incentives, adversarial robustness, privacy, security, and many, many more. So that's it. I'm happy to chat if you have any questions. These are the arXiv links to the papers that I covered in the talk, and some more links to other papers related to distributed SGD.
Thank you so much, Professor Joshi. Before we move to Q&A, let's all unmute ourselves and thank Professor Joshi.
Thank you. Thanks, everyone.
Okay, so we have some time for questions. I have a couple myself, but before that, if anyone has a question, just unmute yourself or raise your hand. Or okay, so we have a question from Shreyas. Shreyas, do you want to ask it directly?
Yeah, sure. Part of the talk you said about like overcoming the heterogeneity by using by taking more number of local steps at the clients which are like slow. So just to ensure the objective consistency.
No, I didn't mean that. So you're not doing more steps at slower clients. You're actually doing more steps at faster clients.
More steps at, oh, okay.
Yeah. So you let clients do as many steps as they can within a time window. But when you average them, you normalize their updates so that the averaged model is not biased towards the faster clients.
Okay. So in the Fed paper, I think you kind of talk about waiting for slower clients to finish their updates for like doing communication rounds on the faster clients, and this might lead to lower number of communication rounds, but the total time which you require to train the global model might still be high because of you relying to finish your updates on the slower clients.
Oh, actually, I think maybe there's a misunderstanding. It's the opposite. So by allowing clients to do as many updates as they can, you are avoiding having to wait for slow clients.
Okay. I think,
yeah, right. So because of that, actually the per round time will reduce by doing this heterogeneous local updates.
okay, I think my question remains invalid now.
Okay, I'll be happy to chat offline if you need more clarification.
Yeah, sure. Thank you.
Mm-hmm.
Okay, any other questions? Okay, so I had one question from a more NLP perspective, which is my background. So in NLP, like there's a big push towards big models and or making models efficient with, but having a lot of parameters. So in that sense, I had a couple of related questions. One, is it practical to like send the model weights or the gradients directly for federated learning, or is it better to like send some kind of an anonymized data instance itself? And the second thing I was wondering is whether the federated averaging is valid when the models get bigger, or whether the federated averaging is valid across different types of models like CNNs versus transformers and so on.
I see. Yeah, that's a really good question. So currently, the implementations of Fed averaging use small or moderate sized models. So it doesn't really depend on the type of the model. It can work both for CNNs or NL language models. But the models have to be small enough such that they can fit within the memory of the of each client, and they can do enough computation. But as you correctly said, like nowadays there's this push towards bigger and bigger models, especially in NLP. There is still ongoing research on this, so it's not settled yet. But one way in which federated learning systems can tackle that is that the global server will have the full model, but the clients will only train parts of it. Maybe they train sparsified versions of it, or partitions of the global model. So if designed carefully, it can be made to work even with large models. And another way is that you can also compress the updates that are sent from the clients to the server by doing quantization, sparsification, etc., to save the communication cost. And I think you also mentioned something about anonymization.
Yeah, I was just wondering whether an alternative could be like anonymizing the text in some way and then sending the anonymized text to the server to do to like directly do a gradient update and
I think that is also a valid alternative. So if the model is too large, but now the data set is small enough, then it might be more efficient to anonymize the data set and send it over rather than like getting all the parameters of a large model and training them. So yeah, depending upon the application, that might be a better solution.
I see. Okay. Okay. I think we have time for maybe one more question. If anyone has any. Okay, if not, let's conclude the talk. So let's unmute ourselves and thank Professor Joshi once again.
Thanks a lot. Thanks
Yeah.
for organizing the talk.
Yeah. So I'll just